Running Python on Fedora Linux is now significantly faster thanks to this small but powerful compiler option. Now, double quote on significant because that's really depends what you think is significant here. In this particular case, it's 4%. In some cases, it's 1.16%. But I want to use this opportunity, this particular news, to open the gates to discuss a very important issue, Nate. And that issue is compiler optimizations. And specifically, something that is well known as function inlining. I want to dive deep into that. How about we dive into this news? News time. The Backend Engineering Show. So this comes from Phoronix, my favorite website for operating systems, hardware optimization news. And let's read the blurb and discuss. Fedora cleared to build Python package with the -03 optimizations. Now, some of you might know what this is. Some of you might not. I'll explain all of this. Okay. The Fedora Engineering and Steering Committee, FESCO, has signed off on the plans for Fedora 41 as the current release. Honestly, I didn't use Fedora much. I used Red Hat and mainly Ubuntu is my main operating system. I know it's not cool to say that, but hey, it is what it is. The other operating system I use is Mac. And at work, it's primarily Windows, uncool as it is. But Fedora 41, you guys, is going to come with a compiled version of Python with an option -03. That means Fedora as a distro of Linux comes with shipped tools, because that's what distribution is. It's just it's a nice bouquet, if you will, of tools on tops of the kernel. Kernel is the best thing. That's the core of this stuff. And I talked about this in my OS. And the distro is just, hey, let's make a nice UI. Let's make a nice GUI here. Let's make partitioning easy. Let's make format stuff easy. You want to get started really, you don't have to run fdisk and figure out all this stuff. What sector to start with? What's the beginning logical sector and what's the end logical sector? You don't have to do all of that stuff. We'll take care of all that with the beautiful UI, And we'll include the curl for you version of curl. We'll include GCC version. We'll include this tool, include Python. That's another option. So here we're looking at a version of Fedora that has Python, but the version prior to that was compiled with a specific option. So Fedora comes with a version of Python, and this Python is, we're talking about cpython, which is the word C means it's written in C, right? So the Python has been written in C, and to compile Python, the interpreter that takes your script, PyScripts, and transpile them and build them into, interpret them. That logic is the interpreter, and that interpreter itself is written in C. Compiling that in C was using a certain option O2, certain optimization. We'll talk about what O2, O1, O2, and O3 in a minute, right? But that's what it is, right? So there is been proposal with 41 to use O3 instead of O2 for better optimizations. What are those optimizations? We'll see all of this stuff. The O3 optimization level is what upstream Python uses for its release builds, and it's proven that it makes Python significantly faster. The significantly faster here I'm reading is between quotes, okay? Across range of benchmark and workloads. So it's already being used in upstream Python. So the Python you download, if you don't have any, if you have Linux and you just installed, you don't have any like Python version, and you install Python from the official repo, then you get a Python that is already compiled with O3 optimization. We're going to talk about what that means. So you get the fast version. It's upstream Python, the vanilla out of the box comes with that. The version that comes with Fedora does not. It's compiled with the more O2, which is considered more stable, you know. So, and they talk about like how is it faster, but what is that? That's what I want to talk about here. So we have O1, O2, O3. These are GCC options, the compiler option, which is it says, all right, if you give me C code, I can compile it with certain optimization, and I'm gonna explain here. So the first option to compile, first, what is compiling, right? What is compile? What is it? What does that mean, right? Compiling is taking a language written in a high level, human readable thing, you know, and pushing it to a specific machine level instructions that CPU, because CPU executes instructions, understands. Yeah? So you compile a C code into this machine language. So one line of code can produce 100 machine instructions, right, based on that logic. Okay, so based on that, we have this intermediary, which is the compiler, and there is also the linker, which actually produces the executables, but it's out of the equation here. So now we have the compiler, we compile, right? So you really need to specify the CPU to actually know what are you compiling against, because compiling against ARM is different than Intel's, different than AMD's, different than, you know, other CPUs that I don't know about. So you need to know the CPU, and you need to know like what is this 32-bit versus 64-bit, because 64-bit means you're going to use 64-bit instruction length versus 32-bit, you're going to use 32 bits. That's 4 bytes versus 8 bytes. Yikes. We're compiling. So this process of translating, so you have the freedom of doing anything you want. I decided to do these sets of instruction, right? This is what I want, my friend. This is what I want. I want A equal 1, B equal 2, right? I want B equal 2 and C equal A plus B. That's what I want. That's the instructions I wrote, right? You will translate them whatever you want, but give me the final output. It does not mean translate one line by line. As long as you get the final output, that's the job of the compiler. And that's where the art of building compilers come. So you then produce sets of instructions. And CPUs work with these local lightning fast memory storage scratch pads called registers. And CPU cannot work with anything outside of the register. Even if you have something in the memory, it needs to put it in the register so that it can pass it to the ALU, right, from the control unit to actually do the math or add or multiplication, whatever the operation is. So you need to be in registers. So you have a scarce resource, and that's called the registers. So you need to do whatever you want, and you have an unlimited resource almost, which is the memory. Memory is just to the compiler, that's the unlimited resources. Like, all right, you can put anything you want there. But the registers is the true scarce resource. Now, if you flip the equations, memory becomes the scarce resource to like a database, right, application. But then the disk becomes like it's an unlimited resource. And when I say unlimited, take it with a grain of salt. It means like it's more ubiquitous, right? So we're compiling. So I want to go through 3 options where the compilers does thing here, right? First of all, no optimization. The easiest way to compile this code to this with no optimization is say, all right, I'm just gonna move, right? And this is assembly, but you can think of assembly as one-to-one as the instruction. So I was like, all right, let's move, I don't know, so R0, move 1 to it, then store R0 to A, which is the address of A, right? Let's just use, I don't know, address like that, right? So I want you to store, I want you to save 1 in R0 and then store it in memory, because the user said, hey, I want an integer A equal this, and an integer b equal this, an integer. That's what when one-to-one would do, right? There's no optimization. It's like, oh, I'm gonna do that, right? This is a hit to memory. You're actually going to the memory, right? And I talk about that. The average hit of the memory, depending if you hit the same row in the DRAM or not, it's 100 nanosecond. You know, that's the cost of going to memory, which can be slow, right? I talk about that in my OS course. But then you do that, and then you say, all right, then move R0 2. Let's store 2 in the same register, and it's okay because we used another register. And let's make it worse. I'm gonna use another register, R0, R1. So for those listening, I really have a very simple program with 3 lines of code. Integer a equal 1, integer b equal 2, integer c equal a plus b. That's all what I want, right? And I'm translating this one by one as a compiler. So I'm moving 1 to a register close by. And then I'm storing R0 into the address of a, which is basically in this case going to be in the stack. So I'm storing R01 in a because the user told me to store it, right? So then I'm going to store 2 in R1, and then I'm gonna store R1 in the address of B. So go and store 2 in B in memory, in the memory location. So another 100 nanosecond. It's less because those two is gonna be in the same row in the DRAM. So you probably open the row, took the hit, and then the second B is in the same frame. So you're probably hitting the same row, right? Especially that this whole thing is a single page, virtual memory page, that is. So now you're doing that. Boom. Then you do, all right, C. We need C. Let's add R3, R1, and R2 and store it in R3. Now you have R3 as the sum of those two. And then you now move, or store actually, R3 to the address of C. So that's what you're going to do without optimization. You translated 3 lines of code to 1, 2, 3, 4, 5, 6. Probably there are a lot of boilerplate instructions that I skipped. But that's basically the gist of it. So what you do, the first optimization, right, which is done with this thing that's called -01, right? The optimization will be, wait a minute, what are you doing? What are you doing? What? You stored 1 in A, but you never used A technically. I mean, you used it to add, but I know what you're trying to do. The output of this whole thing, you just want C to have the sum of 1 and 2. So what the optimization will do is like, all right, we'll do not do this. What is this? Strike through. Can I do strike through here? Come on, Canva. What the heck? Why can't I do strike through here? Strike through. Oh, there you go. There you go. All right, let's make it red bad. Yalla, let's make it red. Yalla. Red. It's like, I'm not gonna move. I'm not gonna move. I'm gonna, well, I take it back. We need to store 1 in R0, right? And then we really don't need to store it in memory. We don't need 1 to be living in memory at all. We don't need it. It doesn't have to be. So we go, oh, no, skip that. So, all right, I'm gonna store 2 in the register, R1. So we have R0 and R1 in the local registers because we have enough registers to work with. And then I don't need to store R1 to B. There is no point of storing B because B is not gonna be used at all, right? Except in one place. So and as far as I look through this, I'll be fine, you know. So I'll do strike through this one. And I'll remove that guy, and then I'll just add these guys on a store. So with this optimization, I remove 2 instructions, and this is a very simple thing. You know, we don't really write to memory if we don't need to, and this is called the local register substitutions. You know, or allocation. So we use, as much as possible, we use local registers. But the problem with this is this only applicable if you have enough registers. So the compiler thinks through, okay, I have this many registers to work with, and I have these functions. So if you have enough registers, you'll work with them. If you don't have, you'll have to go back to memory, store it, save it. It's like working with a temporary variables, right? To work with temporary values, you have to store them and then put them aside and then work with them again. So that's the first optimization. right? And there's like other kind of optimization, like sub-expression elimination. Like if you evaluated a plus b, I'm not, and you later said, oh, a plus b again, you did something like that, right? It will detect that, oh, we have already did this a plus b, so I'm not gonna reevaluate, I'm not gonna do an add again. I know what a plus b is, right? So it will do that stuff, optimization, and will avoid doing an extra add. So these are kind of optimization that the compiler does. Then there's the O2, right? And example of an O2, what we'll do is, and I'm not gonna go through this, so this make the video very long, but essentially it will do function inlining, right? This is very important, but it's going to, but only for small functions. That's all what it does, right? Function inlining is that if you call, right? Let's say this is now, I put this in a function. Let's call it add, right? And this is an add function. And then you have here this main function, right? And then you say, hey, add 1 and 2, add 3 and 4, add 5 and 6, add whatever. You see my point, right? What we'll do is it will replace all these add functions with the content itself, right, of the function, if the function is small enough. Why? Because instead of jumping to this, of course there should be parameters and we're changing these values, but instead of jumping back and forth between completely two different instruction sets, right? Because eventually what will happen is we're going to compile this function into a set of instructions, and we're going to load them into memory, and then we're going to compile this into a set of instructions, and we're going to load in memory, and then the CPU will be jumping back and forth between every time I go to this code and then execute it, and then go all the way here and then execute, and then, oh, I'm done, let me go back and then execute the rest, and then jump back and forth, right? And it's not so bad in this particular example, but what is happening with every function call, there is a cost associated with that, a slight overhead, you know, like you're going to set up the stack frame. Yeah? You're going to, because you're calling a function, you have to save whatever work you have been doing before. Probably like the base point, the old base pointer, the old stack pointers, the return address if need so. And then you need to remember, saving is what, to me, that's the cost, right? You're going back to memory, you're writing to memory, and that's the 100 nanosecond, right? You're doing that, right? So that's one cost. The other cost, which is, to me, that's what it really makes it bad, is you're jumping between different portions of your process memory, and that introduces cache misses. Because you see, CPU loves when it reads something, it reads a beautiful 64 bytes, and then, of course, all of this is living in a 4K page virtual memory. So you're reading sequential stuff. But if you say, okay, read this line, execute this line, but then jump and go all over the way, all the way to line 9901, because my function lives there, happens to live there, go and execute that. Now you lost this beautiful cache that you have on your L1 cache, in L1I cache, right? You just jumped over there, and then you will be causing jumping back and forth, right, between them, and that's the cost. So inlining, what it does, it literally copies this code inside this. So yes, it bloats your code significantly. All right, so it does inlining. So what is the beauty of, if you do inlining, then if you do a read, guess what? Everything is, I'm not jumping. I read something, my function, the code of the function is right there. So as I'm executing main, I don't need to jump somewhere else to execute that. And I don't need to set up a stack frame. I don't need to save anything. There's no function call at all. There's no parameters to pass. There's no overhead of all this stuff, right? And I'm talking about this overhead is too tiny, but it adds up. So you put all this inlining stuff inside, which bloats your code, right? So that's the cost. You gotta get more memory. You're gonna need more memory, but you might get this beautiful cache hit, and that's what what they do here. For O3, that's O2. So what does O3 does? Aggressive inlining. That's what it does. Almost all functions. I don't know exactly how it works. They decide like, all right, I'm gonna do everything. Like any function inlining, almost any, let's just put it, which increases significantly the size of the binary. I'm gonna show you an example here of how Python looked on O2 and how Python looked on O3. Aggressive function inlining. So you increase your size of the binary, that's the cost, but you get beautiful, nice cache hits as a result. Of course, aggressive function inlining can also deteriorate performance because now you're putting your memory, especially in smaller devices, if you have a lot of memory, then you're going to be swapping out, right? If it's too large of a process. And it's not a problem with Python per se, because once you load Python, that entire text area, which is the code, is just mapped once and probably is going to be labeled as not swappable, because that's how I would do it. It's like, I don't swap code. Let's code be hot in memory. And then all processes that are Python and the next Pythons will all share that memory. That's the beauty of share memory, because you're going to share all this memory, and you cannot do this easily without virtual memory. So another thing that O3 does is single instruction multiple data, SIMD, which I talked about on this channel, right? You take one single, as opposed to, instead of doing, let's say you want to add 1 and 2 and 3 and 4 and 5 and 6 and 7, right? So because add always takes like 2 parameters, so you have to add 1 and 2, and then you add 2 and 3, and you have to add 3 and 4. Like, let's say you're adding an array, right? And you're doing all this silliness, right? Doing and summing all this stuff. To do this, you have to do 4 instructions for add. Well, we've seen how it's actually more than that, right? Way more than that. In this particular case, what SIMD does is says, all right, let's use vectors, right? I'm gonna add 1 and 2 and 3 and 4. Well, let's just do 8 here, and I want them to add these 2 vectors, and you use special registers. This only applicable if the CPU supports SIMD, of course, right? So 5, 6, 7, and 8. So you will add all this stuff, and you boom, one instruction, multiple data, fresh. I don't know what that means. Just add over this, boom, optimization. So if your CPU supports instructions, and Python does a lot of stuff, of course. So if you adding arrays, the interpreter will use the version, the SMID version, if it's applicable, of course, right? And you can do, so you'll take advantage of this. So that's why O3 is faster. Now, how fast is this? How fast? Well, before we talk how fast, well, look at the binary sizes here. And for those listening, we're looking at, oh man, let's do math. It's 16,000 kilobytes. It's 16-ish megabyte, let's say 17 megabyte. That's the O2. That's the Python compiled with the O2. But this is old, huh? Guys, this is July 2019. So who knows? Maybe this is more. This is a cpython core developer. Let's shout them up. Inada Naoki. Okay? So this 16 megabyte is the Python O2. And the O3, expectably so, is larger. It's around 20 megabytes. So you're talking 3 megabytes extra, 4 megabytes extra. Is it worth it or not? It's up to you, right? But the benchmarks, well, the benchmark shows, yeah, I found it. So the Fedora project, that's the benchmark we're looking at here, guys. There is a list of the benchmarks, the 223 async generators and all of that stuff, and mostly all of them are like 1.04 faster, 1.09 faster. So you're saving few millisecond here, 100 millisecond here, 100 millisecond there, 200 millisecond here, 200 millisecond there. It's just all adds up. And guys, by the way, if you're not on Fedora, this doesn't affect you at all, because you're probably using a version upstream which already compiles with that option, right? So you're safe, essentially. You're good, right? And yeah, but I thought I'll talk about that because it's just interesting to understand all these, compiling options. But yeah, that's what I want to talk about. O1, O2, O3, for the cpython interpreters, and I'm gonna reference all. I'm gonna reference all of this stuff for you guys to read because I gotta credit everybody here. This is good. The news is not that, it's meh, and I've seen the comments. People don't seem to like Fedora for some reason. They seems like Fedora was not innovating enough, and they were making fun of this article. But I loved learning a new thing. This O1, O2, O3 optimization. I knew about the optimization themselves. I didn't know about these levels, to be honest, right? So I spent some time researching, and I love it. I love it. Anything software engineering, love it. Love it. See you on the next one, you guys. Check out my operating system course oni desne. oscourse.win. That is oscourse.win. A shortcut to direct you to Udemy directly with a beautiful coupon. And enjoy it. Over 20 hours, you guys. 21. I added some more lectures. 21 hours. I spent 2 years working on that course. I learned so much. And you will see my enthusiasm in that course. And you probably get sick of it. But hope you check it out. Thank you so much. See you in the next one.